Welcome back, everyone. So we are now here to continue our course on quantum mechanics. And today we open up a very important chapter. And this chapter will provide a discussion of the fundamental aspects of quantum mechanics that was completely skipped until now. Remember, a few lectures back, we had collections of rules of quantum mechanics that incorporated most of what is needed in order to describe the behavior of matter at the microscopic scale, but not everything that is required to describe the behavior of matter at that scale. There is one fundamental piece of information about quantum mechanics that we did not discuss, and this is precisely what we will unpack today, and it's the notion of spin. You must have heard the word spin of a particle, especially in conjunction with what is called the Pauli exclusion principle. Those of you who have a chemistry education must have heard about that. But the spin of in quantum mechanics is actually much more fundamental than the Pauli exclusion principles, and it roots it into complicated aspects of symmetry, of space-time, and all that. We should not be discussing all this interesting, fascinating theoretical physics aspect of the origin of spin. But we will sort of tackle this problem from a more phenomenological point of view, and try to enucleate the basic aspects of it that are needed in order to describe spin from the quantum mechanical point of view. And then we're going to postulate one more rule of quantum mechanics. And I guess that would be the last rule we will need to introduce, which has which will lead as a byproduct Pauli's exclusion principle that is so important to understand structure of many body systems, in particular atoms and molecules, from the quantum mechanical point of view. So, without further ado, let's go and dive into the subject. I will immediately go into my whiteboard, and let's get our journey into quantum spin started. So in our phenomenological introduction to spin, we want to start for one fundamental piece of observation. If you take quantum mechanical particles, and by particle I means objects that are whose wave function, if you want, is confined in a small region. Sometimes this region is so small that you cannot even resolve it, like the electron. We don't know whether there's some inner structure of the electron or if it's point like, we know that with any current resolution, experiments were not able to resolve any structure of the electron, for instance. In other case, my particle could be an atom, and therefore could be actually an effectively point-like particle which does have some inner structure, or a nucleus which does have some inner structure, or a proton or a neutron which does have some inner structure. So at this level, we should not make the distinction whether a particle is fundamental, meaning that for as much as, as far as what we know today, it doesn't possess any inner structure, or if it's composite, and so that, it's a small bound state of some inner constituents. We call a particle whatever has a definite size. And if it has a size, it will look like a particle when I look at that as distances much larger than the size. Okay? And what is the observation? That if I build a and I throw a bin of such particles, of identical particles, say a bin of the same type of atoms, a bin of the electrons, a bin of protons or neutrons, or, well, basically three things. Oh, sorry. Only one of the following things is observed in experiments. So only of the following scenarios are realized in experimental setup. Scenario one, this is my Stagg-Gerlach, which, as you know, determines conventionally the z direction. It could be the x or y, but let's choose it to be z. Scenario one is that the particle goes through the Stagg-Gerlach with no deflection. Which means that a particle that has zero component of the magnetic moment, because it's a point particle, and we can imagine it to have basically either vertical or negative deflections in this inhomogeneous magnetic field. Remember, this is not a constant magnetic field. I put an arrow here to remember that in the Stagg-Gerlach, this is in fact a gradient of magnetic field that is producing interaction. Let's not worry about the experimental details of the Stagg-Gerlach. And then if you rotate the apparatus, then you immediately realize that this same information propagates to any component. So there are particles, that's what scenario one is telling us, that have no magnetic field. Fine, that's, just a piece of information that might be interesting or less interesting, but that's one possibility. The scenario two, well, let's not write scenario. So let's say, let's just list a, if for saving space. The scenarios two is when I shoot my particle, I see the famous double deflection that I discussed at the beginning of this course. And remember, once I do see a double deflection, then I'm not allowed anymore I'm not anymore allowed to measure more than one component because of the uncertainty principle. So the second scenario is one in which I have two possible values for the magnetic moment component along the z direction. And then in other cases, what people have observed is a threefold scenario splitting. So I would say mu z is equal to plus some mu up, 0 mu, and minus mu naught. And, going on and on with the phenomenology, in principle, you could think of observing particles which have a fivefold splitting. So it appears from this set of discussions that the y component, the z component of the magnetic moment is quantized. It can either be zero if there's no magnetic moment, but if there is a finite magnetic moment, then it can only be observed in quantized steps. Now, this piece of information can be combined with other pieces of information other pieces of information we already know from this course. In particular, we know that magnetic moments cannot be mutually observed. So in other words, that if I measure mu x and mu y, this might not be zero, and the same happens between mu y and mu z, and the same happens between mu z and mu x. They are all non-zero. How do I know? Because remember what the discussion at the beginning of the course, I throw particle, I orient the tangent like in one dimension, I observe some splitting, then I make a measurement in a different splitting, and then a measurement in the original splitting. So what I observe, remember, in my Stengerlach, first splitting, I'm going to draw this schematically, not realistically. By this, I mean something that measures the x component. You get two splitting, and if you measure again the z component, you would expect to have already measured the z component, that you get only one deflection upwards, so to say. But what you actually observe is, again, equal upwards and backwards splitting, which implies that the measurement along the z direction has destroyed the information about the previous measurement about the x direction, has destroyed information about the measurement along the z direction, or in other words, the mu x in this case and mu z do not commute because you cannot find a common set of eigenstates to both operators. Okay, this is a piece of information that is important. And somehow, this piece of information can be, you already begin to build an analogy with another discussion we had in this course quite recently, which was the discussion of orbital angular momentum. Remember, when we were discussing the orbital angular momentum, we were deriving this set of rules So orbital angular momentum was a quantity that displayed two identical features compared to what we did see here. You can either be in a situation where there was no orbital angular momentum whatsoever, or if there was an orbital angular momentum, then you can only measure one component at most of the angular momentum. And as far as the corresponding eigenvalues of this component, they would jump at finite quanta from the top from a maximum value to a negative of that maximum value. Or stated mathematically, remember, if I have a finite quantum number L, which is associated with the eigenvalues of L squared according to this equation, these are the eigenvalues of L squared, then you would get eigenvalues of a corresponding nz going from minus L plus 1 all the way to L plus L. And this is somehow very similar to what we see in the Stangella, because we saw that either you get total deflection when go up, or in some cases you get a total deflection times down, or you get, 3, or you get an even or an odd number of discrete steps. Now, in the case of angular momentum, you always have an odd number of values of L whenever there's non-zero values, but in general. Why? Because, for orbital angular momentum, it's important to specify that, if L is equal to 0, then I get only M0. If L is equal to 1, I get 3 values. M is equal to -1, 0, 1. If L is equal to 2, M is equal to minus 2, -1, 0, 1, 2. So it's going to be 1, 3, 5, and so on and so forth. So this is the only difference we observe with respect to the Stangella, because in the Stangella we get either no splitting, which is the, in no splitting, this would be the analog of the M equals 0, L mu z equals 0, which would be the analog of L equals 0, M equals 0. Or we get triple splitting, that's fine, that would be analog to this situation, but we also have double splitting, and there's no counterpart in this analogy of the double splitting component. But other than this puzzling difference, we only are here to say that the eigenvalues of this operator and their Newton computational relationships reflect somehow some fundamental analogy with what we observed from orbital angular momentum operator. Is just a coincidence? Is there anything deeper than that that connects these two seemingly different quantities? The magnetic moment of a particle on one hand and the orbital angular momentum moment of a quantum particle on the other one? Well, if you think a little bit in terms of physics, you'll discover that, in fact, there is some connections between the two. Because you see, if you have a classical charge, so if you build a classical picture, which is just for us to think, you cannot rely on a description of nature based on a classical picture, because the classical picture is not a description of nature. But we can still think about this classical picture for a moment to sort of get some inspiration. And the inspiration is that if you take, say, an orbitating particle, and this particle has a charge, let me call it Q, and you make it, for instance, you build a particle going around an accelerator, obviously, even if it's just one particle, it will create a current, an electric current. And this particle orbitating will obviously have an angular momentum, because that's what angular momentum is all about, rotation, right? Now, it will have an angular momentum, but since it's charged, it will create a current, and since it will create a current, it will create a magnetic field. And to be more precise, any orbitating circuit will create a magnetic moment. We'll have a magnetic field with a magnetic dipole moment. Which means that basically the field that will come out from here, the magnetic field lines, will be in this kind of a configuration. That's what a dipole moment looks like. Oops. Okay. So, in some sense, you see, if instead of throwing a quantum particle into a Stern Gerlach, if instead of throwing quantum particle into a Stern Gerlach, we had been throwing little circuits into a Stern Gerlach in this, purely fantasy-driven ideal experiment. Well, if I were to do that, then we would expect, in fact, to see always an odd number of splitting, because we would have a corresponding orbital angular momentum, and the magnetic moment would have been proportional to the angular momentum through what is called mu naught, is sometimes called the magnetic moment. Anyway, it would have been proportional. I mean, I don't want to go into dimensionality issues. Let's say proportional through a constant on L. So in particular, the Z component would have been proportional to LZ, and therefore, since Z is quantized in triplets or in oddlets, so let's say either 1, no orbital momentum, or 3, or 5, or 6, then we would expect that. So in some sense, it makes sense that the orbital angular momentum is associated with some intrinsic, so that the magnetic moment we observe in Stern Gerlach behaves like orbital momentum, because we know that if there is angular momentum, at least orbital angular momentum, there must be magnetic moment. But there are things that quite don't fit in this picture. In particular, we don't understand the double splitting, because the orbital angular momentum does involve also, only involves oddlets, 1, 3, 5, and so on. But we, at least from this very classical picture, a very naive hand wave argument, we see that it is quite natural that we see analogies between magnetic moments and what we had seen in orbital angular momentum, because finite angular momentum will generate a magnetic moment. So the two things are basically proportional. And even if if thinking about the small circuits, like a wire band onto itself with a circulating current, looks a little bit too artificial for you, you may think of having a sphere rotating along, say, one axis. And you still will have you can think about this as an infinite amount of small circuits. If you have electric charge on the sphere rotating, then you'll still generate a current and you still generate a magnetic moment. So maybe this idea of a little circuits propagating is too artificial. Then think about a particle with a sphere rotating along some direction, with an electric charge distribution. So this little moment. So so we are tempted, looking at this analogy, to say whatever we see like a point-like particle, it's not really a point-like particle, it's actually some rotating current. Well, this would explain why we see the splitting and the destructiveness of the measurements and all that, but it will not explain the splitting into even beams, 2, 4. So how can we explain the splitting into an even number of beams? Well, the only way to do that if you think hard about it, is, or at least the simplest way to do that, is to assume that L angular momentum can be half integer. For instance, if L was 1/2, and we just keep everything else as in the theory of orbital angular momentum, if you only allow a half integer orbital angular momentum, so to say, then we would have these two possibilities, explaining therefore the double splitting. And if L would be 3/2, then we would have 3/2, 1/2, minus 1/2, and minus 3/2, therefore explaining the quadruple, the quadrufold splitting. Oh, that fits fantastic with the only major problem that there are no orbital angular momentum eigenvalues with half integer principal quantum number L. Orbital angular momentum only has integer quantum numbers L. So we cannot entirely explain this phenomenology without making additional I would say, without introducing an additional law of physics that states something new. We cannot explain this observed phenomena entirely relying on concepts that are already there in the theory. We have to introduce more physics law. And in particular, therefore, we must conclude that the intrinsic magnetic moment of particles is associated, if you want, to an intrinsic kind of angular momentum, which, however, is not the standard orbital angular momentum, because the equivalent of L, which will soon take a different name, can be half integer, can be integer as well as half integer. And the idea is to call it differently, since it's not the orbital angular momentum. So we define a lot, when I talk about angular momentum in physics, in classical mechanics, I only have the orbital angular momentum. But in quantum mechanics, and I use a different color to denote that this is true only in quantum mechanics, and it's not there in classical mechanics. We have an additional type of angular momentum, which is called spin. And spin means to rotate, for those who are not native speakers, like myself. So this name is somewhat reminiscent of this classical picture that it's like if this had anything to do with effectivist particle, where intrinsically point-like rotating particle with no dimension, yet everything goes almost as if there was a spinning sphere, but not exactly a spinning sphere, because a spinning sphere would have odlets separating spin beams. So it's almost like a spinning particle, but it's not a spinning particle, and people have called it spin anyway. So spin is one of the most misleading concepts, because the name spin comes from our empirical reasoning, and it has survived in spite of the fact that there's probably nothing spinning in there. Because if it was really something spinning in the classical sense, there would be only certain quantum numbers, but more than that is observed. So it's just an intrinsic property of particles. So what do we know about everything we said about spin? Well, first of all, we know that, the magnetic moment is proportional to the spin of a particle. And I will, write it as an operator because it only exists in quantum mechanics. So we might as well call these three different operators. So that's one fact we know. The second fact we know is that these spins behaves like the orbital angular momentum in terms of destructiveness of measurements. So we can, postulate the same law, blah, blah, blah. So let me just I think, I'm not sure whether I was missing, no, that's okay. And, but now, the third piece of information we know is that, I have S and a Z, that's my set of maximally commuting operators. And therefore, I can define the eigenstate of spin to be given by two quantum numbers, S and SZ. This is the equivalent of L, and this is the equivalent of M. But now, S can be both integer or half integer. So this is the new piece of information. And we should see that this new piece of information, that is the fact that the spin principal quantum number S can be both integer and half integer, is in fact responsible for so much unexpected phenomena in the microscopic world to make it a fundamental ingredient of nature. The existence of half integer spins is really what shapes the largest part of the structure of matter, especially in the condensed phase. I come to that, of course. Most of this course will be, from this point on, strongly relying on the existence of this. So in general, this division is so important that particles can be divided in two categories. Those with the integer spin, so with S equal 0, 1, 2, or 3. These are different particles because remember, the spin is an intrinsic property of a particle. You cannot change the particle of the spin while maintaining the same particle. The spin of the particle is like its mass. If you double the mass of the electron, you get another particle. I've never heard of anybody getting a different mass. I mean, it's not something we have discovered, but say the electron and the proton, let alone that the proton has a finite size, but let's suppose we don't know that. They are, if we didn't know that the proton has a finite size, then of course the positron, that is the copy of the electron with positive charge, and the proton would be completely identical if not for their mass, right? Now, but they call differently because the fact that two particles have a different mass is considered important difference that basically distinguishes two particles. So a particle can only have one of these. So, some particles have spin 0, some particles have spin 1, some particles have spin 2, and, in principle, particle can have higher spins, but having particles with very high spin becomes less and less frequent in nature, and they're all composite particles in the end. Or spins can be integer, half integer, 2/3, 3/2, 5/2. And again, when you go to higher half integers, then typically you end up being composite particles. So the particles with integer spins are called after Indian physicist Bose, and they are called bosons. While particles with half integer spins are called after the Italian physicist Enrico Fermi, and they're called fermions. So let's see, can we recognize some of these particles? Let me make some example. The electron is a spin 1/2, so it's a fermion. The proton and the neutron, they are all spin 1/2 particle. The photon is a spin 1 particle. There are particles with spin 0. Yes, you probably don't have been exposed to their existence in the past. For instance, subatomic particles called pions that are important in nuclear physics. Well, they are spin 0. Sorry. Yeah, spin 0, sorry. But there are particles, subatomic particles of spin 1, and subatomic particles of spin 3/2, for instance, the famous delta plus, the delta barium. These are all subatomic particles. You can hear about them in this lecture and forget about them for all practical purposes that your quantitative biologist life will ever imply, because you're never going to be sensitive to nuclear physics in quantitative biology. So, but just for you to know that there are examples for basically most of these different values. Some of, if even nuclei or atoms, even nuclei or atoms can be considered as particles with different spin. For instance, if you take suppose you have a particle with spin 0, like a pion, orbitating around the proton. They are so-called pionic atoms, just for you to know. Then, since it has no intrinsic spin, but it could be charged, it would generate through the orbital angular momentum a magnetic moment. Now, if this pion proton system is sufficiently small, and if you look at it from very much afar, you will not be able to resolve whether it's point-like or if it has two components, one orbitating around the other. All you will be able to see is that it has a magnetic moment. And depending on what is the orbital angular momentum of this pion, it would be perceived as a different particle with a different magnetic moment. So this is all to say that composite particles, depending on the relative motion of the composers on the components, are perceived at low resolution from afar, so to say, as different particles. Is this sounding strange to you? Is it sounding strange to think that what we consider a particle depends on how high resolution we look at the particle. You see, if I look at the particle from the very low resolution, and I see that it has, maybe I see two of them with different spin, but basically the same mass, I would be probably tempted to say that these are two different particles. Because I don't know whether this is, these magnetic moments they have comes from an intrinsic spin or comes from the orbital angular momentum of the components, because I cannot tell whether they are composite particles or they are point-like particles, because I haven't had the resolution to look into them. Now, suppose with decades, people developed the technology to look into particles, distinguish. All of a sudden, they realize that many particles that look as different particles at low resolution, they were in fact the same physical system at different levels of excitation. So in other words, for instance, you take the hydrogen atom in different L equals 0 or L equals 1 state, and if you look at it from afar, it will have basically the same mass, the same charge, but different magnetic moment, because the orbital magnetic moment will be different. So if you don't have the structure, don't have the technology to look into this hydrogen atom to a point to recognize that it's not a fundamental particle, it's made by an electron and a proton, you would say there are two particles, let's call it hydrogen 0 and hydrogen 1. They are very similar masses, but one has 0 angular momentum, and the one has 1 or 0 magnetic moment, and the other one has a finite magnetic moment. But then if you look at these systems with high resolution, you discover that these are not two different particles. They are the same particle, but one is an S state, maybe it's a ground state, and the other one is a P state or a D state. So going up in energy allow you to look into smaller and smaller objects, because when you go up in energy, you can resolve smaller and smaller distances, because in order to resolve small distances, you have to probe the system with a higher and higher momentum. And therefore, sometimes by looking at the system with very high momentum, people were able to discover that particles that look different, at least on the basis of their spin, they were in fact the same particle in different quantum states. And this process is called unification. Sometimes unification is referred to the fundamental forces of nature, electromagnetic unification, electroweak unification, or unification of particle species into combination of a fewer number of constituents. Typical example of unification is the Mendeleev periodic table. You look at the Mendeleev periodic table, you would guess there are hundreds of different fundamental particles called atoms. But then, if you study more, then you discover that actually all of the periodic table can be explained assuming there are only 3 particles: the electron, the proton, and the neutron. And different combination of this particle and different level of numbers of them will produce the entire Mendeleev table. So what we have done so far was to introduce the concept of spin, the commutation relationship of spin, and the fact that, by looking into systems with a given spin, you might discover that if the system is composite, then maybe systems that look different in terms of some quantum numbers, they might be actually composite systems made by fewer components arranged in different ways in terms of quantum numbers. Okay. So the last thing I want to discuss today is how do we mathematically represent spin 1/2 particle. Well, to represent spin 1/2 particles, we need a very simple mathematics, because the quantum state, as far as this spin is concerned, the quantum state of a spin 1/2 particle, it's represented by two quantum numbers. One is S, which is fixed, is 1/2. And the other one is the component, which is plus 1/2 of minus 1/2. So there's the Hilbert space of the spin states of a spin 1/2 particle is only two-dimensional. So we can represent this as a regular R2 vector space. For instance, we can, associate this state to this vector and this to this vector. That's a good representation. So this is the abstract space, and this is its actual mathematical representation. And then now we need three operators, xs, sy, sc, which obey the commutation relationship of the angular momentum. For instance, sx, sy equals of I h bar sz, and are 2x2 matrices because they act on the two-dimensional vector space, and such that these states are eigenstates of Sz. So if you think about this for a while, you come out with the answer of what this matrix should be. And I give you the answer and convince you that they have all the properties. These are called Pauli matrices. So in other words, a mathematical description of spin is given by, as z equals, associate the SV equal plus 1/2 to say one vector this, as z equals negative 1/2 to the opposite vector, and then you build the following matrices. You associate SZ to h bar half sy h bar half 0 I negative I 0 0, and as z h bar half 1 negative 1 0 0. So why are these matrices the correct representation of these operators? Well, let's convince you. First of all, let's start from the easy part. SZ is certainly a good representation because if I apply SZ onto the plus 1/2 state, I get 1/2, 1/2. Let's check it. H bar squared, H bar. Spin is quantized in units of H bar, if you remember, for orbital angular momentum. So I get like H bar 1 minus 1 acting on 1 is equal to H bar half 1, and H bar half 1 minus 1 acting on the other spin states is giving me minus H bar half over 2, 1. So at least we have checked that this is the correct operator that has these states as eigenstates with the correct eigenvalue. And the other two matrices, you can convince yourself that this is a good representation and this is a good representation simply by evaluating the commutation relationship. For instance, let's evaluate Sx, Sy. We need to find out that this is equal to IH as Z and all the other three, right? So this will give us a certain number of relationship of matrix elements. And if you combine how many constraints there are, then you discover that you have completely identified. You have as many equations as you need to completely and uniquely identify all the entries of this matrix. And then You're done, basically. These are the metrics for 2x2 representation. So let me help you check this. I do Sx, Sy minus Sy, Sx. This will be H bar half 0, 1, 1, 0, 0, I, negative I, 0, negative H bar half 0, I, negative I, 0, 0, 1, 1, 0. And if you work out the algebra of these metrics, you'll discover that these are actually equal to H bar half squared 1 minus 1, which basically means you have proven this relationship. And if you do that with all the others, you'll discover that all the commutations relationships you want to satisfy are actually satisfied correctly. So basically, you have demonstrated that Pauli matrices are in fact the right two-dimensional representation of spin 1/2 particle. So the spin of an electron and of a proton can be completely understood, spin states of an electron and a photon, by introducing simply two-dimensional matrices. So if I want to understand the quantum state of a particle which can move in the space, then I need an infinite dimensional vector space, because I know the wave function is a Hilbert space with infinite dimension. But if I have a particle that is fixed in a point and anything that can change it is its spin, maybe it's an electron attached to an atom, for instance, then this particle, to represent the quantum state of this particle, I will need only a two-dimensional vector space. In the most general case, such as an electron, the electron can be, freely propagating in space. So I will have, so to say, my spin of the electron. If this can freely propagate in space and have a spin, then I will have to use a mathematical representation that is involving both position and spin. That means that my wave function, let me call it psi, I will put the arguments in a moment, will be the projection of this quantum state, let's call it phi, onto both position and z component of the angular momentum. So that means that there will be one function, I can call it as z of x. If this is plus 1/2, this will be 1/2. And this is negative 1/2, this would be negative 1/2. So in other words, you can say that the state of a spin 1/2 particle is represented by both components, but two functions, not just one. One function associated with the up component, and the one function is represented by the negative component, and these objects with two components is called a spinor. Okay, tomorrow we'll dig more about spinor, retake this concept into consideration, develop it a little more further, sort of rediscuss it from the scratch, and see, some examples perhaps. Okay, good for now. Thank you for your attention. See you tomorrow.